Hello guys, welcome back to my channel Gamma Di Gamma. So in this video I wanted to continue with our multivariable calculus streak. So we did multivariable limits and multivariable functions in the last video. In this video we're going to talk about multivariable derivatives. Yes, and we have a lot to discuss. So let's get started. First, let me give you a preview to what the definition of a derivative was in single variable calculus. So if f was a single variable function of x, the derivative with respect to x of f of x was the limit as h goes to 0, f of x plus h minus f of x divided by h. Now, in single variable calculus, this definition of the derivative was basically said that a derivative will only exist if you take the limits from both sides and it gives you the same answer for the derivative, which means the left hand derivative and the right hand derivative are the same, and that's when the derivative actually exists and takes the value that both of these take up. If they're not equal, then the derivative doesn't exist. We had functions such as the absolute value of x that were evidence that although the function is continuous, it's not differentiable at x is equal to 0, for example. So we sort of want them to be smooth if we're talking about differentiability. Now in multivariable calculus, for example, if you have function of two variables x and y, we have a partial derivative with respect to one of these variables. We have this curved d to represent that it's a multivariable function. That is defined as the limit as h goes to 0, f of x plus h comma y minus f of x comma y divided by h. Now what this does is when we're differentiating partially with respect to x, we're just having we just have an increment there, an infinitesimal increment there, not in the other variable. So there's a clear independence, and in the similar way you can define the partial derivative with respect to y as the limit as h goes to 0 of f of x comma y plus h minus f of x comma y divided by h. And again, the existence of these partial derivatives, similar to the single variable calculus case where limits taken from any directions in this definition, they needed to exist, they needed to be unique. So whatever, in this case we're not just restricted to the left hand and the right hand side, so called. We have every other direction to worry about. If you recall my previous video, that's how we guaranteed whether a limit exists. We checked for all directions. So instead of seeing that limit taken in each direction gives one single value for every direction irrespective of the direction, what we can do is we can always check for it to be 0 when we subtract the derivative from this definition itself. It should be 0. Just to elaborate on what I'm saying, let's say we have a subset of Rn, U is a subset of Rn. I'm writing this more generally for an input space that is n dimensional. Let's have function that maps points in U to points in R. So you can think about this as a n n-dimensional input space scalar field, because it's mapping to R, not any other higher dimension. So what we can do is, let's say we have x as a point inside U. You can think of x as a vector that has n components. So we want to see whether f is differentiable at A, and A again is a point in U. All these points are in the domain, which is U. So what we can do is we can check whether limit as vector x approaches vector A, or f of x minus f of A minus d of f of A times x vector minus E vector divided by the magnitude of x vector minus A vector. We need to show that this is 0, and that's when we know that a derivative exists. And then the derivative of f of x is d of f of x, if this is true. And then what is d, you may ask me? Well, it's in this case, in the case where we have a scalar field, so as to speak, d of f of A is just a matrix. It's a 1 by n matrix of the partial derivative. So partial f of, say, x1, that's like the first variable for this n-dimensional input space. So I mean, you keep doing this and evaluate them at A. Since it's n-dimensional, we'll end up with a x sub n. So whatever this matrix is, it's a 1 by n matrix for this case, scalar field case. That's what we put in here. And to be precise, to be just clear what I mean by x is just x1 to xn. Okay, that's a column vector. Same thing with A. You can split A, you can write A like this, is a column vector with all of its components. And this matrix is what we call the Jacobian. The Jacobian matrix. This is going to be really helpful for us when we are changing coordinate systems, but right now just think of this as a representation of all the possible derivative cases. So if we apply this on x minus A, we're basically should get this difference quotient, and then that's when everything will become 0, and that's when the derivative exists. The partial derivatives exist. If this is not 0, then there's some issue with the partial derivatives, that they don't exist. That if you take this limit in some other direction for some partial derivative, you're not going to get a unique answer. That's what that means if it's not true. Now, so we can also define a quantity called the gradient of f, say at a point A in this case. That's just this guy, the Jacobian, but you write it down as a column vector. I mean, this was just a matrix, and this became a column matrix. But for a gradient, we want to think of this as a column vector, a vector. So I mean, if you want to use some subscript summation notation, which I was not planning on introducing in this video, because First, we need to understand what the partial derivatives and gradients are. But I mean, if you want to say x1 f at a, e sub x1, for example, that's the unit basis vector in that direction. So this clearly shows you that this is a vector. That is precisely the gradient evaluated at a of f. Let me just write that down. This is the gradient of the function f. And now the thing is, if we have, what if we had a vector field? So what if we have, say, f which goes from u, where u is a subset of Rn, as I stated before, but instead of R, it maps to Rm. What do we do now? Well, the definition still stays the same, except maybe now you'll just have a zero vector. So we'll have the same definition as above, but it will just equal the zero vector, which belongs to Rm, because that's what it's mapping to, right? And the Jacobian now will still be defined the same way, except it will now be m by n matrix. Because now we have to differentiate each component of, like, whatever. Okay, so the way I think about this is, there's the output we have for f has like m components, and we need to differentiate those m components with, with respect to like those n variables that we had in our input space. So that's, if you can try to visualize this, how this is going to work is that we have, say, f1 to fn is like, what do you get as your output, for example? Each of these are functions of x vector, each of these components. But when you like differentiate this, you need to like differentiate them. We need to differentiate each. So you'll have df1 d partial x1, and this is still the first row, by the way. And then you keep doing this until you reach m. So partial fm with respect to x1, partial fm with respect to xn, and this will make it an m by n matrix. So the way we're doing is we're differentiating each component with respect to those n input space variables, and we do that for those m components. So I hope this is clear now. Before moving on, and this is like a definitive condition that we have for the existence of the partial derivatives. Now, let me just give you a small example of how to practically calculate what's going on, how to practically find out partial derivatives. So if you have a two variable function, which is basically x cubed plus 2x squared y plus 3y squared, find the partial derivative with respect to x. 3x squared plus, I believe this will be 4xy. So the way you calculate the partial derivative with respect to x is you treat y as a constant. You treat y as a constant. And then the way you calculate partial derivative with respect to y is you treat x as a constant similarly. So the first term will become 0. We will have 2x squared for the second term plus 6y. And that's how you calculate partial derivatives, and you can repeat this process for n dimension, any number of dimensions in the input space. So this was an introduction. Now let's look at more general properties, because even though this object here, this definition says that partial derivatives exist, it's not sufficient. It's not a sufficient condition to say that the function entirely is differentiable. Because as you will see, we don't just want the existence of partial derivatives, we also want the continuity of partial derivatives. So if partial derivatives exist, they also have to be continuous in order for the function to be entirely differentiable. And I'm gonna probably give you an example up next, where where this issue comes up, where the partial derivatives actually exist, but the issue with the continuity. I won't prove the theorem that says that this is the essential condition for differentiability, but I'll show you. I'll try to give you some intuition. Okay. What I can do before turning the page is I can just find the Jacobian for you guys at a general vector x. So that's gonna be, take all of these guys, 3x squared plus 4xy and 2x squared plus 6y in the first row. Well, we can find the gradient similarly, because this is a scalar field. Gradients are only for scalar fields. Let me emphasize that here. Gradients, at least the way we're defining now, are only for scalar fields. For vector fields, we're gonna have a little complicated concept. It's not gonna be a column vector. It's gonna become a tensor, and we probably cover that in the future. So I mean, just for the gradient in this case, just take all these and write them as a column vector. That's how easy this is. So let me just do an example just to drive home the point. If we have f of xy, some function which is defined as follows. It's xy divided by x squared plus y squared when xy is not equal to 0, because if you want to calculate the limit at 0, it doesn't exist, because it depends on the direction of approach. And 0 when x and y are equal to 0. So that's how you define f of xy. What we can do is we can just use the first. We can try to calculate the partial with respect to x. We need to check whether this is differentiable. At the point 0, 0. So first calculate the partial derivative at 0, 0. Naturally, we have the limit as h goes to 0, uh, the function which is this guy at 0 plus h comma 0, so that will be 0 plus h times 0 over 0 plus h squared plus 0 squared minus the function at 0, which is 0 by the definition, divided by h. I'm just using the definition of the partial derivative. If you calculate all of this out, it will be 0. Fair enough. Now partial with respect to y, we can do a similar approach here. Again goes to 0. So this means the partial derivatives exist because we calculated you calculated them using the definition. Okay, both of them are 0. So partial derivatives exist here. There's no dispute about it. Okay, now let's check for that start condition. If you remember that start condition, that condition was, well, f of at x minus f or at whatever point minus the Jacobian at that point times x at minus a vector divided by the magnitude of x vector minus a vector in the limit that x vector tended to a vector, and all of this we wanted to be 0. I think in the last slide I made this slight error when I said that this wasn't a definitive condition. This is the definitive condition because this makes or breaks the differentiability of a function. If this is true, then it's always going to be, the function is always going to be differentiable at that point. If it's not, then which means there were some problems with the partial derivatives, and in this case there will be a problem. Spoiler alert, but yeah, that's why I chose this example. Okay, now we know our point is 0, so we want our x and y to approach 0. F of x is just xy divided by x squared plus y squared minus 0 minus, well, we found out the partials, so that makes this matrix of the Jacobian to be 0, 0, applied or dotted with just x vector, which is this guy, divided by, now the magnitude calculated this way, square root of x squared plus y squared. This is just Euclidean space definition of this induced norm because we already have defined this inner product. We want this to be 0. Now, okay, so let's calculate this, whatever this is. Let's use polar because that's how we try to do stuff, at least with x squared plus y squared in both scenarios, so it's convenient to work with polar. This is just multivariable limits, guys. Just see the last video for this. If you do some calculation, this will become r cubed, and this goes to infinity. It does not go to 0. It diverges. So this function is not differentiable because this is not 0. This in our case is not 0. So the f of x and y at 0, 0 is not differentiable. Well, you might ask why is there this problem? Because the partial derivatives were clearly existing. I mean, we calculated them. We got finite values for both of the partial derivatives. So why is there still a problem with, why is the function not differentiable? That's because try to calculate the partial derivatives at any other point apart from 0. Fine, partial derivative with respect to x at some arbitrary point xy will just be, well, you can do the quotient rule on this guy, treating y as a constant, and you get the following. y cubed minus x squared y divided by x squared plus y squared, the whole thing squared. And since this is at an arbitrary point, it's fine. What if now we try to take the limit? What if we try to take the limit as x and y approach 0 for this partial derivative? If we try to do that, you can try to do that if you want. Again, use polar coordinates. You have an r cubed factor and an r to the fourth factor. So in the limit that r goes to 0, this r to the fourth factor will dominate the r cubed factor, and it will again diverge to infinity. So if you take the limit of the partial derivative from some other point to 0, you're ending up with infinity, although the partial derivative at that point exists. This is just an issue of continuity. So it's not continuous. It is not continuous because at that point you have a different value and the limit is giving a different value. So there's this this jump discontinuity, if you want to think about it that way. If you try to do the same with the y, well, you calculate it at any point, the partial derivative, you get x cubed minus xy squared over x squared plus y squared, the whole thing squared. And if you try to take the limit as x and y approach 0, 0, you again end up with some r cubed factor on the top and r to the fourth factor in the denominator, which again diverges. So again, even the partial derivative with respect to y is not continuous, although it exists, although it has some finite value at that point. If you take the limit from some other point to 0, approaching 0, it just diverges. So it's non-existent. It's not continuous. Yeah, more than non-existent is not continuous. So that's why you see this condition is so important. Every time if you want to see if a function is differentiable or not, you should just check whether this is 0, and that is a definitive condition. Otherwise it's hard to check for all the partial derivatives and then all the continuity of the partial derivatives. More than just finding them out, continuity of partial derivatives was important. So this gives us this important statement: a function is differentiable if and only if its partial derivatives exist and are continuous. So there you have it. I hope you kind of see what's happening here, because there's like this disjoint, there's this big issue with that you want the partial derivatives to actually exist at that point. Otherwise, it's similar to like the constraints of a multivariable limit. It's just extended onto partial derivatives. So you want them to be continuous, otherwise because of this limit issue here later on, this limit issue here. I like to think about it that way. Okay, we plotted scalar fields before. I hope you know how to do them. Just set the scalar field equation equal to a constant. Then you get a good idea of the z profile of that scalar field, at least. What if you have capital vector field f that maps points in R2 to points in R2? So you can write this out as x and y is equal to, say, x1, f1 of x and y, f2 of x and y, two components. Now what we can, so this is a vector field, because your output space is not is two dimensional. It's not r, it's r2. And as I said, you can't really define a gradient of this guy in terms of in like in elementary terms. You need to introduce the notion of tensors. Okay, so what we can do is the way to plot this, I forgot to tell you, is to take each component, say f2 x and y divided by f1 of x and y, and set that equal to dy over dx. Because if you remember what vectors were, like if you remember how to calculate the angle between if you wanted to calculate the angle between the x-axis and the vector itself, this angle here, what you did was theta was just the inverse tangent of whatever this guy was, this y component divided by the x component. So I'm using the same principle here, but I'm setting it at to dy over dx because that's the slope of the tangent vector. If you have some vector field, this way, the tangent vector at each point, which I'm gonna probably represent with these arrowheads, well, the slope of these tangent vectors with respect to the x-axis, for example, that's basically what your dy over dx is, except I'm doing this for a more general, I'm doing it for like a general tangent vector. So that's why I'm setting them equal to each other, because this guy will give you the direction. So if you're at some point x, y, if you plug that into this vector field, it will give you a vector at that point. Assume your vector is like this. You do this this component quotient here, you get the slope, you get basically the tan of theta here, if you take the tan on both sides, which is the slope of this. And what's the slope? It's just dy over dx, right? And at that point, so I hope this gives you a better intuition of why to do this. Now we can do one example quickly. F of x and y, assume that's x squared plus y squared. Well, this is a scalar field. What we can do is, if you want to plot the scalar field, set this equal to constant, just call it, I don't know, k squared. And then what is this? This is the equation of a circle. So these level sets are going to be circles of varying radii, of radii k, radius k. So it's going to look something like this. And now let's calculate the gradient, because a gradient is a vector. So gradient will give you a vector field. That will just be 2x, 2y. Just take the partial derivatives with respect to x in the x component and with respect to y in the y component. And how to plot this? Well, I just told you. 2y over 2x is dy over dx. You solve this differential equation, you get natural log of x is equal to natural log of y plus constant c. So x is equal to c naught times y. So we have basically lines of varying slopes, straight lines of varying slopes. So you have something like this. Okay, and one thing that's important to note is the gradient is always perpendicular to its respective scalar field. So if you take a scalar field and you take the gradient of that, the gradient will always be perpendicular to the respective scalar field. You can check this for this case. For these curves, you can, I think, parameterize it with using polar coordinates. Actually, when I mean it's perpendicular to scalar fields, perpendicular to the tangent vectors that of the scalar field. So the scalar field, position vector of the scalar field, you can represent as k cosine theta, k sine theta for a given k. Dr, that's now going to be your tangent vector, is negative k sine theta, k cosine theta. Let's call this tr, not dr. Tr. Okay, if you clearly do the dot product, you'll see they're perpendicular to each other. And if you dot this with now the gradient vector, so the gradient will now under this parameterization look like 2k cosine theta, 2k sine theta. If you dot this guy with this guy, you'll get 0. So in this case, you can see that they're perpendicular. They're always going to be perpendicular to each other. This is generally a true fact. Okay, let me do this last exciting example from physics. So if you have a dipole, which is basically two charges, and an ideal dipole is when this length between them is practically 0. I don't know how you can visualize this, but please try. So now the electric potential because of this dipole is a scalar field. So you define it as the dipole moment vector dotted with position vector divided by 4 pi epsilon naught, where epsilon naught is the permittivity of free space, magnitude of r cubed. That's how you define it. And for this case, our given case, we're choosing r to be just in general xi e sub I hat. I'm using subscript summation convention. And p is just in one dimension. It's just p times x3 hat. So it's in the z direction. Now, okay, fine, we can simplify our scalar potential. We get px3, because it's a dot product, 4 pi epsilon naught, magnitude is just x1 squared plus x2 squared plus x3 squared raised to 1/2 power, which is the square root, and we have a 3, so we'll have 3/2 power here. Now this is a little hard to calculate, because if we want to plot this scalar field, we need to set this equal to some constant c, and solving this out, finding the locus of this or what equation this is hard in Cartesian. So what we do, we convert to spherical. So x1, let x1 equal to x be r times sine theta times cosine phi. I hope you know how to define spherical coordinates. If not, don't worry, I'll cover it up. Right now, just accept this parameterization. So if you plug all these things in, PR cosine theta divided by 4 pi epsilon naught, well, this will just be r cubed is equal to c, which means that we have established an equation between these guys. So r squared is basically p cosine theta over c times 4 pi epsilon naught. And then you take the square root, you get a polar equation in r and theta. You can graph this in your polar calculator, fine, whatever. That's how you sketch the scalar field. Now, the vector field, because the vector field you can generate by this scalar field is by taking the gradient of the potential scalar field. But the thing is, the negative gradient of the potential is the electric vector field. That's how it's defined. There's no dispute about this. It's just the definition. Now, the way to calculate the gradient of this crazy function in Cartesian is really hard, and if you convert whatever you get as the electric field from Cartesian to polar or spherical, it's gonna look bad. So what I did, and I'm not gonna show it because it's lots of steps, I directly took the electric. I wrote, I took this final simplified case of the scalar field, electric potential, and then took the gradient of it in this polar coordinate in r and theta, because that's how it was much easier to do, and I got an expression in r and theta. So I had a component in the r hat direction and a theta hat direction. Then I basically took the ratio with its and set them equal to d theta over dr. I solved the differential equation. I got something like this: sine theta is equal to e to the r over 2 with the proper constant c naught. And I'm not gonna show you how to calculate the gradient in different coordinate systems because I haven't touched on them yet. But when we do, I might even revisit the calculations that I did here. For now, just accept this calculation. And just to give you an intuition, if you know electrostatics, you know the electric field of a point charge, of a positive charge, always radiates from that point charge. So if you use that, you might expect the electric field to basically be somewhat like this: start at the positive, end at the negative, be all this like webbed structure. And the potential, since it's always perpendicular to the electric field, to look something like this, these equidistant lines or something like that. And this is just because we know of that the electric field due to a positive charge always radiates from the positive charge. This is because we know this. But what if we don't know this? What if we were working with this for the very first time? What if we were the original physicists who were actually doing this? Of course, we didn't have graphing calculators back then, but assuming we did back then, we can prove that this, whatever we expect, is actually the reality, because we can graph this now. So let me just show you the graph quickly. Okay, so in this part of the video, I'm showing you the graph. So the red, what I've done in the red is just those equipotential lines, those scalar fields of the potential, the electric potential. Those are the red lines, and these are quite as we expected. These two green lines that were represented with equations are basically the electric field. I had to take into account the positive and negative because this natural log function is not really, doesn't play well with negative things, negative quantities. So as expected, assume there's like a point charge here, and since it's an ideal dipole, the distance between those two charges is like 0, so it's almost like one big charge here, except there's this pinch here to denote that they're actually two charges, but in the limit that the distance between them goes to 0. Otherwise they wouldn't be this, it wouldn't look like this pinched off place here. So the electric field lines, think about them, go and end, start and end, start and end, start and end. And if you notice, they're always perpendicular. I might want to zoom in here. See this tangent vector is always perpendicular to this electric field vector, and that's true at any point where they intersect like this. So this is really what the electric field and the electric potential of an ideal electric dipole system looks like. So I really hope you enjoyed this video, guys. Please like and subscribe to my channel. Stay tuned for more content, and I'll be sure to give you lots of content over this summer. So stay tuned and take care. Peace out.